Alrighty, in this video, we're going to be talking about Chapter 10, Correlation and Regression. We're only going to be talking about the first two sections, um, really just kind of getting to scatter plots and correlation and regression lines and things like that. Just really understanding the definitions of it, what they are. We'll go into a little detail, but not too big of detail. Your next statistics course will definitely go into further detail of these things. All right, here we go. So, another area of inferential statistics involves determining whether a relationship exists between two or more numerical, that is, quantitative variables. For instance, is there a relationship between a person's blood pressure and his or her age, or is there a relationship between the size of a house and its appraised value? We will investigate whether there is a linear relationship between the variables. If so, what is the strength of the relationship? What type of relationship does exist? And what predictions might be made from the relationship? So that's pretty much the gist of this chapter. In 10.1, we talk about scatter plots and their correlation. So our first objective here will be to learn how to draw a scatter plot for a set of ordered pairs. In simple correlation and regression studies, data from two numerical or quantitative variables are collected to study whether a relationship exists between the two variables. The data are collected as ordered pairs. One variable is the independent variable, and the other is the dependent variable. The independent variable can be manipulated, is known as the explanatory variable, and is called x. The dependent variable, which cannot be controlled or manipulated, is known as the response variable and is called y. The researcher decides which variable will be considered the independent variable and which will be the dependent variable. Sometimes one variable can be assumed to affect the results of the other. For instance, the hours a student studies for an exam is likely to have an impact on the percentage of correct answers on the exam. In this case, the hours studied would be the explanatory variable, and the percentage of correct answers would be the response variable. However, when considering a relationship between one's income and one's height, it is not clear which should be independent and which should be dependent. So the determination is arbitrary. The independent and dependent variables can be plotted on a graph called a scatter plot. The horizontal axis is labeled with the name of the independent variable, and the vertical axis is labeled with the name of the dependent variable. The coordinates of the axis are determined by the smallest to the largest data values of the variables. So a scatter plot is simply a graph of the ordered pair as x comma y of numbers consisting of independent variables x and the dependent variable y. The scatter plot is a visual way to describe the nature of the relationship between the independent and dependent variables, even if the scales are not the same. Researchers look for positive linear relationships when the data points increase from left to right. Negative linear relationships are when the data points decrease from left to right. Curve linear relationships or other non-linear relationships or no relationship at all when the scatters show no pattern, line, or curve. So a graphically here you can see that if I have some scatter points here and I go from left to right, you can see I have a positive slope of a linear line. So this would be a positive linear relationship. You can see if I drew a line of these scatter points, I would have a negative slope. So this would be a negative linear relationship. And then you would notice on this one, I can draw some type of a parabola. So that would be a curve linear relationship. And then here, it's so scattered, I can't make a line, I can't make a curve, I can't make anything. So we can indicate that this right here would have no relationship. So those are some graphical few points with the definitions that we now have. Procedures for drawing a scatter plot, just like we saw in the definitions. The first thing you would do is draw and label the X and Y axis. Then we would plot each point on the graph. And then step 3, determine the type of relationship, if any, that exists in the variables. All right, so that's a lot of definitions and stuff. Let's do our first example here. So in example 1, we're going to look at absences versus final grades. So we're going to construct a scatter plot for the data obtained in a study on the number of absences and the final grades of 7 randomly selected students from a statistics class. We have student A missed 6 times and made an 82 as their final grade. Student B missed 2 times and made an 86. Student C missed 15 times and made a 43. Student D missed 9 times, made a 74. Student E missed 12 times, made a 58. Student F missed 5 times and made a 90. And then student G missed 8 times and made a 78. So to draw a scatter plot, you would draw and label the X and Y axis and label the relationships of the size of the variables. So when given a table like this, it tells us that our X is the number of absences and our Y is the final grade. So when I come over here to make the scatter plot, you can see that my X-axis is labeled as number of absences and my Y-axis is labeled as final grade. The next thing you need to look at is what is the smallest X value? Hopefully you see that it's a 2. And then you see that the largest X value is a 15. So when you come to the x-axis, you'll see that because I went from 2 to 15, it was a lot easier just to go from 0 and then just go up 1 every time. But then when you look at the final grades, the lowest grade I have is a 43, and the highest grade I have is a 90. So you can see that I don't need to do 10, 20, and really and truly, I don't need to do 30 because my first number is not until 43. So I can go 40 and then I can go up by 10. So where you start doesn't matter. Just make sure that you're going up by the same amount every time. And they stopped at 100, even though 90 was our highest, because typically 100 is the best grade you can make. And then after that, also notice they gave the graph a name. So absences and final grade. That's very big. After that point, then we can then plot each point. So each point would be a coordinate. So student A would be 6, 82. Student B would be 2, 86. Student C would be 15, 43. And then you can see that student D is 9, 74. Student E was 12, 58. Student F was 5, 90. And student G is 8, 78. So then I can see all of my points. The third thing to do is now we need to determine the type of relationship, if any, exists. So you can see in this example, there appears to be a a negative linear relationship. So if I could probably draw a negative linear line that would go through these dots or relatively close to these dots. So therefore I can see that it's definitely a negative linear relationship between the number of absences and the final grade as a percentage of the student, which logically makes sense. The more you miss, most likely the lower your grade. Now, is it 100%? No, because there were some that did pretty high and still missed quite a bit. All right. So that's one that's kind of done for us. Let's look at another one. So in example 2, we're going to look at the number of teachers in the thousands and number of pupils per teacher. So it says a researcher wants to check for a relationship between the number of pupils per teacher and the number of teachers in thousands employed by a school district. The data are from randomly selected samples. So we can see that school district 1 had 7,000 teachers and 12.4 students per teacher. School district 2 had 34,000 teachers and 14.3 pupils per teacher. District 3 has 9,000 teachers with 14.3 pupils per teacher. School District 4 has 8,000 teachers at 9.2 pupil or students per teacher. District 5 has 16,000 teachers at 18.3 students per teacher. District 6 has 15,000 teachers at 12.1 students per teacher. District 7 has 6,000 teachers at 12.3 students per teacher. School District 8 has 14,000 teachers at 12.4 students per teacher. District 9 has 32,000 teachers at 15.2 students per teacher. And District 10 has 10,000 teachers at 13.4 students per teacher. Most of this must all be 6A schools. All right, so here again, we're going to go through step 1. So we'll draw and label the x-axis in relation to the variables. And then notice it does not give us the x and the y. So typically the left column, so this is when it kind of gets a little arbitrary if not told. So the x, there's usually the first column here. This is just the name of the school districts, but this will be the first column that matters. And this would represent your x values. The second one will be the y value. So basically the number of teachers or the number of students per teacher is dependent on how many teachers that district has. So this would be the independent, and then this would be the dependent. So when I draw out my scatter plot, I start off with my X and Y axis. So this will be my X, this will be my Y. I'll name this the number of teachers in the thousands. And then this right here would be pupils per teacher. And I see that a number of teachers range from 6 to 34. So I think what I'm going to do is I'm going to go by tens. So I'm going to go 10, 20, 30, 40, and 50. And then I see pupils per teacher. I got 9.2 all the way to looks like 18.3. So I think I'm just going to go by fives. There we go right there. And then I'm just going to graph it. So I got 7 and 12.4. So it's about roughly right there. 34, about halfway up to 14.3. So maybe almost up there. 9, so about right inside at 14.3. So roughly the same distance. And then I got 8, so a little bit more inside, but 9.2. So that'd be more like right here. Then I got 16 up to about 18.3. Then I have 15 about 12.1. That's probably about right there. And then I have 6 at 12.3. So maybe about right there. And then I have 14 at 12.4. So probably about right there. And then I have about 32 up to about 15.2. And then I have 10 at about 13.4. So roughly about right there. So now that I have it all labeled, don't forget to give it a name. So this will be the number of teachers in thousands and number of pupils per teacher. Step 3, now we're going to determine the type of relationship, if any, that exists. Though really and truly, when I look at this, I don't see much of anything. I might be able to argue maybe a positive, but it looks like it could maybe, this is just really hard to tell anything. So what I'm going to go with is in this example, there appears to be no strong positive or negative. There might be maybe a very weak positive, but not strong. Not enough for me to make an assumption here. So there's no strong positive or negative linear relationship between the number of pupils per teacher and the number of teachers in thousands in a school district. Now, your interpretation, you might be able to say maybe there's a weak positive relationship, but really, if I had a little bit more data, I bet you anything this is going to maybe start turning. Maybe we could have a curve linear. It's just not strong enough for me to determine either one direction. All right, so that's how you build scatter plots. So let's look at our second objective, which is to compute the correlation coefficient. If I'm looking at a graph And it's kind of my interpretation of what I see, unless it's just super strong. Is there a mathematical approach that I could go with that would tell me, all right, here's the result. This is what you can say. This is strong. This is weak. This is a positive. This is a linear, just based on math. And there is. We can actually look at the correlation coefficient. So let's look into it. So in this one, the correlation coefficient measures the strength of a relationship between two variables. So our definition here, a population correlation coefficient, is that the population correlation coefficient, denoted by this P-looking thing, I think it's called phi, actually. I think it's written like this, is the correlation computed using all possible pairs of data values x, y taken from a population. A linear correlation coefficient is denoted by R, computed from the samples, measures the strength and direction of a linear relationship between two quantitative variables. We can use the Pearson product moment correlation coefficient, or PPMC, as well. All right. So let's break these properties down. So the properties of a linear correlation coefficient is that the correlation coefficient is a unitless measure. Does not have a unit. The number just means something. The values of R will always be between -1 and 1, inclusive. So that means that -1 and 1 could be an answer, and everything in between. If the values of x and y are interchanged, the value of R is actually unchanged, because all the R does is just tell you if there's a correlation there or not, regardless of which one is X or Y. If the values of X and Y are converted to a different scale, the value again of R is unchanged, because again, just gives you a correlation between the two things. And then number 5 is that the value of R is sensitive to outliers and can change dramatically if they are present in the data. So you got to realize that if we're trying to determine our correlation coefficient and we have a couple of outliers here, instead of getting a nice line here, we might actually get a line more like this. So outliers will definitely impact your correlation coefficient. All right, so let's look at some different examples of what graphs could look like. So you'll see here, these are potential graph scatter plots. So instead of just being positive or negative, we can actually go a little bit more here. So if R is a 0.5, you can see it's a little bit more spread out. If R is a 0.9, it's actually a little bit closer together. If R is a perfect 1, it's a perfect linear line. And then the opposite works as well. If this is a negative 0.5, you can see that it's going to be going down, but it's really scattered. A negative 0.9, again, more condensed and it's scattered, but still definitely can tell it's going down. And then a -1 is going to be a perfect negative linear line. So that's what these little R's would represent. Without us actually having to graph it, we could calculate the R and determine our strength and determine if there's a correlation or not. So assumptions for the correlation coefficient, just like in most of our assumptions, we have to assume that the sample is a random sample. The data pairs fall approximately on a straight line and are measured at the interval or ratio level. The variables have a bivariate normal distribution that is given any specific value of x, the y values are normally distributed. And given any specific value of y, the x values are normally distributed. That's what by Varte normal distribution means, is no matter what x or y's are given, we can assume that they're normally distributed. Be sure, though, to check that the assumptions are met when the exercise does not state that they hold. All right, so we'll start off, just like we always do, with a formula to help us figure out our correlation coefficient. So as you can see, it looks pretty intense, but we'll do it together to kind of help you out. But this will be the sample times the sum of the product of x and y minus the sum of x times the sum of y, all divided by the square root of the sample space times the sum of x squared, or your x's squared, minus the sum of your x's that are squared, all times the sample times the sum of your y's squared minus the sum of your y all squared. Right? And this looks like an intense thing, but once you fill out a table and figure out all the answers, then it's just a bunch of plugging in. So again, n is the number of data pairs, and we're going to round r to 3 decimal places. So here is our procedures to finding the values of the correlation coefficient. So step 1, we're going to make a table labeled as x, y, find our product, find our squares, and then we can find our sums. Step 2, we're going to fill out the table. So we're going to place the values of x in the x column and the values of y in the y column. Then we're going to multiply each x value by the corresponding y value and place the products in the xy column. Then we're going to square each x value and place them in the squares in the x squared column. And then we're going to square each y value and place the squares in the y squared column. And then we're going to find the sum of each column. And then once you have all these numbers, it's just a bunch of plugging and chugging. So if, for instance, again, in step 3, we just substitute the values into the formulas, and then we just calculate our R. Again, n would just will be the number of data pairs, and we'll round to 3 decimal places. So let's put this into practice. So in example 3, we're going to look at those absences and final grades. So for the data in example 10.1, we're going to compute the linear correlation coefficient. We already have the data and have noticed that the scatter plot has a negative slope, but we want to back it up with a more mathematical approach. So most of this is already done for us. We're just going to just see how it's done. So you can see every x value was plugged in the x, every y value was plugged in the y, and then mathematically they took the x times the y and multiplied it all the way down. Then they took each x value and squared it, put those products all the way down, took each y value and squared it, and put the results all the way down. After that, we just added each column. So we added our x's, added our y's, added our products, added our squares of x's and our squares of y. And then you can see in step 3 here that all we're going to do now that we have all of these numbers, we're just going to simply plug it in. So there were 7 students, right? 1, 2, 3, 4, 5, 6, 7 students. So that's my n. So I plug a 7 in. My sum of my xy was 3,745 minus my sum of x times sum of y. So that's 57 times 511. If you plug that in the calculator, it does come out to negative 2,912. And then on the bottom here is just going to be the square root of 7 times the sum of x squared, which is 579, minus 57 squared, and then 7 times this number minus 511, which is the sum squared. And then I do that, and I get this number, and then I divide the two, and I get this number. So again, all of it's just plugging in. So once you calculate it, you can just easily just type it in the calculator to get the result. And as you can see, this is a negative 0.944 we already knew it was a very strong negative correlation. And because that is so darn close to -1, we could back up our argument that it's definitely a strong negative correlation. So we can see the linear correlation coefficient suggests a strong negative linear relationship between the number of absences students have in class and their final grade. That is, the more absences a student has, the lower the final grade will be. So we already assumed that when we did our scatter plot. Now mathematically, we can see that it holds together. All right, let's do the next one together. So we'll do the number of teachers in thousands and the number of pupils per teacher. And then we'll be using the data from 10.2 and we'll compute our own correlation coefficient. And I think what I'm going to try to do here, see if I can put this on one page to help us out. Let's see. Okay. All right, that'll be my step 3, and then I'll just type it here. All right, here we go. So I'm with my X values and then plug it all in. Again, I'm just trying to get it all in one space. So my X's were 7, my Y's was 12.4, 34, and 14.3, 9 and 14.3, 8, 9.2, 16, 18.3, 15, 12.1, 6, 12.3, 14 and 12.4, 32 and 15.2, and then 10 and 13.4. So when doing this on the homework, it's going to be a small set of numbers, so you're not there all day. Bigger numbers, calculator can do most of this for us. All right, but I'm just going to simply multiply this, and I'm going to see something real quick. I guess I'll let y'all see it with me, but then I'll lose it. I'm going to see if I can type in my information. Just going to try one set and see what happens. Hmm. What if I do A times B? Okay. All right. So I'm going to do it with us. All right. So let me share my screen real quick. Make sure you are seeing it as well. Okay. So here we go. So I'm going to come back and start all the way over. I was just curious if it would do it. So if I go to list and spreadsheets like I normally do, and I type in all my X values, and again, that was 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, let me go with my Y values in. All right, so if I want to multiply those, all I got to do, I don't have to name it X or Y. I just got to say, all right, I want you to take column A times column B, and it'll multiply them all for me. So now you can take these numbers and simply just plug them in all the way down. And on the next part, it says I want the x's squared. So if I just go, I want you to take my A column and I want you to square each number, hit enter. Again, it'll square each one for me. So I got all my numbers there. And in that last column, it wants me to square all my y. So this time I'll say B and I'll square them. And I can see that it'll square all those numbers for me. Now I'm curious if I write an equal sign here, if it'll do it for me. Let's see, equals the sum of A. We'll see what happens. So that stinks. Gotta undo what I just did. Okay, so we'll just delete those. Alrighty. Wonder if I just say sum of A here. So sum of A. It does. Okay, so in a weird way, I can do my sum of my first column. So I'll do sum of A, which is 151. And then I'll do sum of my B, which are my Y values. And it gives me that. And then I can do sum of my C column, which will be the product of X and Y. And it gives me that. And then I can do sum of my D column, which is the X squared numbers. It'll give me my sum. And then I can do the sum of E column, and it will give me my sum there as well. So the calculator can definitely do a lot of it for you. And then we can take those numbers and then we can plug it in. So if I come back to this area here, I lost all those numbers, but you can definitely plug them all in. And for sake of argument, I'll just kind of do it for you so that you also have a good example as well. But you saw that the calculator will definitely do it all for you. All right, so that's all the numbers that the calculator just gave us. And then it also gave us the sums. So now I'm going to take those sums. I'm simply just going to plug in. There was 10 as my sample. And then the sum of X and Y is 2,117.4 minus my sum of X, which was 133.9. That's my sum of Y, which was, oh, that should be a Y. So this was actually 151 times 133.9. I'm going to divide all of this by the square root of 10 times 3,187 minus 151 squared, and then 10 times 1844.33 minus 133.9 squared. And then you just simply just type that straight into the calculator. And when you do, you get this as your answer. So R would equal 0.442. So you can then argue, see, I was right. It does have a positive correlation. And you could really argue it, but my argument was more that it did not have a strong positive. And I can see, since it's less than 0.5, it is definitely, you could argue a positive correlation, but I would almost say because it's less than 0.5, this is most likely a weak positive correlation. And the closer you are to zero, the more of a no relationship there is, by the way. All right, so that's how you can do it by hand, or using the calculator definitely help you out to get most of your answers real quick. All right. So let's look at our third objective here, which is to test the hypothesis or the null hypothesis that the population would equal zero. So the correlation coefficient is between -1 and 1. When R is close to either -1 or 1, the linear relationship is strong. When R is near 0, the linear relationship is weak or does not exist. Because the value of R is computed from the sample data, there are two possibilities where R is computed from sample, so where when R is not equal to 0. Either the value of R is high enough to conclude that there is a significant linear relationship between the two variables, or the value of R is due to chance. All right. So assumptions for testing the significance of the linear correlation coefficient is, again, the datas are quantitative and are obtained from a simple random sample. The scatter plot shows that the data are approximately linearly related. There are no outliers in the data. The variables X and Y must come from normally distributed populations. The null and alternate hypothesis are that the population does equal 0. There is no linear correlation between X and Y. Or the alternate hypothesis is that the population does not equal 0, and there is significant linear correlation between X and Y. We will discuss three methods to test the significance of the correlation coefficient. The first is the traditional method and uses the t-test. The second uses the p-value. And the third uses table I, or table 1 there, to find the critical, I think it's table I, the critical value of R for a specific degree of freedom in a given significant level. So the formula for t-test for the correlation coefficient would be t equals R times the square root of n minus 2 divided by 1 minus R squared, for the degree of freedom equal to n minus 2, where n is the number of ordered pairs. So notice it's n minus 2 now than what we've been seeing in chapter 8. The traditional method of hypothesis testing of significance for R, we would state the hypothesis, find the critical value of T, compute the test value, make a decision, and then summarize the results. The p-value method of hypothesis testing of significance of R, you would state the hypothesis, compute the test value of T, find the p-value, make the decision, and then summarize your results. So looking at example 5 here, it says we're going to test the significance of the correlation coefficient from example 10.3. So if we test the significance of the claim that there is a linear correlation between the absences and final grades, well, given that alpha is 0.05, we rounded our R to negative 0.944. And you can see that we first state the hypothesis. So we're saying that P is equal to 0, which just simply states every single time almost there is no linear correlation between the number of absences and final grades. And then our alternate hypothesis basically states it's not equal to 0, and there is a linear correlation between the number of absences and final grades. So that's going to be pretty much your hypothesis every single time. It's going to be there is no, and then there is a linear correlation between blah and blah. So if we look at the first method, which is the traditional method, we find the critical value of T. So for the degree of freedom, we do 7 minus 2, which equals 5. If you use table E, or the T distribution table, which might be F, you would see that it's at plus or minus 2.571. You'll compute the test value, because again, you would go to 5 of the degree of freedom and 0.05, and you just go there, and then that would be your answer. Again, if it's negative that you're looking at, it'll be the positive and negative version of it. We will then compute the test value. So then we would plug in our R times the square root of our degree of freedom divided by 1 minus the R squared, and we get this negative 6.398. So since this value is less than the negative 2.571, which was the critical value, we would therefore then reject the null hypothesis, stating that there is a correlation. And so then step 5, you can see that we can finalize with there is sufficient evidence to support a significant linear relationship between the number of absences and final grades. And again, we already kind of knew that. But again, this is just now a way of putting it all together with our hypothesis testing. If we went with method 2, which was the p-value method, again, you would compute your t-test as normal, but to find the p-value using table F, we can see that the p-value is going to be less than 0.01. If you happen to use technology, you find out it's 0.0014, but that's not what we're looking at. We can just simply look at table F using our test value. We can see that's definitely going to be less than 0.01. And since the p-value I get is less than 0.01, which is less than the alpha 0.05 we were looking at, I can tell that therefore we would also reject the null hypothesis, once again stating there is sufficient evidence to support the significant linear relationship between the number of absences and the final grade. All right, so let's look at example 6 here. There you go. So in example 6, it says test the significance of the correlation coefficient from example 10.4. For the number of teachers and the number of pupils per teacher data, test the significance of the correlation coefficient and use alpha of 0.5. I don't think it matters which process or which method you choose. I find method 1, the traditional method, to be a little bit easier to understand. So that's kind of what I'm going to focus on. So we can see that step 1 here is we need to state the hypothesis. And our null hypothesis, again, will always be that the P is equal to 0, which states that there is no linear correlation between the number of teachers and the number of pupils. The alternate hypothesis basically states that it's not equal to 0 and that there is a linear correlation between the number of teachers and the number of pupils. And then if we go to step 2 here, we need to take our R, which we got from example 10.4, ended up being 0.442. So that method was already taken care of. Now we find our T value. So our degree of freedom is going to be 10 minus 2, which gives us 8. So when you figure out our T, pull that up on a different page real quick. It takes me a little bit to download the book real quick so I can go to the correct table. Which is table F. So I'm going to switch over. We're going to lose all this, but I'll start right back here. So make sure you have it as well. So again, I got the degree of freedom of 8, so I need to go all the way up to 8 here. Here's 8. And then I would go to, we need 0.05. Right? What was the alpha? 0.05. So we got 10 minus 2, which is 8. There it is right there, 0.05. And so therefore I get 2.306. So then that means that my t-score would be plus or minus that. So again, on step 2, again, you already have step 1 written. I'm not going to rewrite it. But step 1, I'm going to use that R coefficient or correlation coefficient of 0.442. We calculated our degree of freedom as 8. So therefore our T ended up being plus or minus 2.306. So now on step 3, we will compute that. So T would equal the 0.442, which again, just so you know, the equation was R times the square root of n minus 2 divided by 1 minus R squared. So when I do this, again, I'm going to go R times 8 divided by 1 minus 0.442 squared. And when I type that in the calculator, I actually get 1.394. So now in step 4, I got to make a decision. So we're going to make a decision. And since my 1.394 is less than 2.306, it does not fall in my critical value range. So therefore, I don't know, we do not reject the null hypothesis. All right, so because that 1.399 was less than the 2.306, it doesn't fall in my critical region. It stays in the safe zone. So I am too paranoid. I would be incorrect by more than 5%. All right, so with that said, we just then summarize this. So step 5, we will summarize it. And so for my results, I would simply just say there is not sufficient evidence to support a significant linear relationship between the number of absences and final grades, which again, we've concluded already, but now we have even more evidence to back up our case. Alrighty, keep trucking along. So we do have possible relationships between variables. So when the null hypothesis has been rejected for a specific alpha value, any of the following possibilities now can exist. There is a direct cause and effect relationship between the variables. That is, X causes Y. For example, water causes plants to grow. Poisons cause death. The heat causes ice to melt. The second thing we can see is there is a reverse cause and effect relationship between the variables. That is, Y causes X. For example, a researcher may believe that excessive coffee consumption causes nervousness, but it may be that nervous person craves coffee to calm his or her nerves down. The third thing we can see is the relationship between the variables may be caused by a third variable. For example, if a statistician correlated the number of deaths due to drowning and the number of cans of soft drinks consumed daily during the summer, he or she would probably find a significant relationship. However, the soft drink is not necessarily responsible for the death, since both variables may be related to heat and humidity. This third variable is a variable that researchers does not know about or that is not accounted for in a study and is actually called a lurking variable. I guess I kind of wrote it there. The fourth thing we can see is there may be a complexity of interrelationships among many variables. For example, a researcher may find a significant relationship between students' high school grades and college grades, but there are probably many other variables involved, such as IQ, hours of study, influence of parents, motivation, age, and the instructor. The fifth thing we can see is that the relationship may be coincidental. For example, a researcher may be able to find a significant relationship between the increase in the number of people who are exercising and increase in the number of people who are committing crimes. But common sense dictates that any relationship between these two values must be due to coincidence. So there is a little bit of caution here. When averages are used instead of individual data, the results may be a higher correlation that actually exists. Results of correlation studies using averages cannot be generalized to individuals because averaging tends to smooth out variability among individual data values. So even if the correlation between the two variables is significant, it does not imply causation. That's a big statement there. Even though our evidence might show that it is, It just shows that there's a correlation, but does not show that it's a causation. All right, so that's a good place to stop in this video. The next video will be 10.2, talking about regression lines, which will actually be our last video. As always, if you have any questions, feel free to reach out and let me know. I'll see you in the next video.